Welcome. In topic 3102, we focus on urban flood resilience with an emphasis on pluvial flooding, those intense rainfall events that overwhelm local drainage and create rapid surface inundation. The goal is to connect climate signals, urban form, and infrastructure capacity with the modeling workflows designers and planners use to make better decisions. As we go, keep in mind that flood resilience is not only an engineering exercise. It is also an urban design problem because streets, parcels, and open spaces determine where water goes, what gets exposed, and how quickly a city can recover. So we will keep translating between two languages, the language of models and metrics, and the language of design choices you can actually implement. Here is today's roadmap. First, we establish why urban flood resilience matters now, and why pluvial flood risk is rising in many cities. Second, we build the conceptual foundation, the hazard exposure vulnerability logic, the data layers models rely on, and a practical modeling workflow you can reuse. Third, we broaden from hydraulics to risk assessment and adaptation options, gray infrastructure, blue-green or nature-based measures, and policy tools. Finally, we translate modeling outputs into design decisions and look at two best practice case studies to ground the concepts in real-world applications. You should listen for a recurring theme. The best workflow is the one that is defensible and fit for the decision you are trying to make. By the end of this session, you should be able to do 5 things. 1. Explain core concepts and performance criteria used in flood-resilient, climate-responsive design. 2. Interpret how urban form and ecosystem services interact with climate data to shape pluvial flood risk. 3. Outline a GIS and simulation-based workflow, potentially including digital twin-style iterations, to analyze scenarios. 4. Compare structural, nature-based, and planning responses as part of a resilient system. And 5. Argue for interdisciplinary, socially inclusive decisions, because flood risk is unevenly distributed and adaptation choices can either reduce or deepen inequities. Urban floods are increasingly a design problem because 3 drivers are moving in the same direction. Climate change is shifting rainfall extremes, short duration, high-intensity storms can produce disruptive runoff even when the total daily rainfall is not unprecedented. Urbanization amplifies that signal. As impervious surfaces expand, infiltration decreases and runoff volumes rise. Flow also accelerates because smooth surfaces and connected street networks quickly convey water toward low points. At the same time, many cities rely on aging drainage networks that were built for historic design storms, with limited storage and capacity. The result is that flood losses are governed not only by rainfall intensity, but by where water accumulates, which assets are exposed, and how rapidly essential services, mobility, electricity, healthcare access, can recover. This is why pluvial resilience is simultaneously a planning, design, infrastructure, and governance challenge. When a road underpass ponds for 2 hours, the key question is not only, how deep is the water, but, which neighborhoods lose access, which jobs and schools are disrupted, and who cannot safely relocate or recover. Performance-based design reframes the problem. How does the place absorb water, route it safely, store it temporarily, and then return to normal function? To work rigorously, we need shared definitions. A hazard is the rainfall runoff condition capable of causing inundation. Exposure is what lies in harm's way, people, buildings, and networks located where floodwater can reach. Vulnerability describes how sensitive those exposed elements are and what adaptive capacity they have, whether they can resist damage, recover quickly, or avoid harm through preparedness and resources. Risk is the outcome we ultimately care about. Potential losses, disruption, downtime, and the recovery burden. A useful check is to imagine the same storm hitting 2 areas, a commercial district with flood-proof basements and backup power, and an informal settlement with fragile housing and limited drainage. The hazard may be similar, but vulnerability differs, so risk differs. It is also helpful to distinguish flood types. Pluvial flooding is rainfall-driven surface flooding when local drainage and storage are exceeded. Fluvial flooding is river flooding that overtops channels and floodplains. Coastal or compound flooding involves storm surge, tide, river flow, and rainfall interacting. In this topic, we emphasize pluvial processes because they are tightly linked to street design, parcel storage, and the spatial pattern of imperviousness. Urban form controls how water moves. Imperviousness is a first-order factor. Sealed surfaces reduce infiltration and increase the volume and speed of runoff. But street-level flooding is often controlled by microtopography, curbs, road crowns, driveway dips, and small depressions that steer overland flow toward specific hotspots. Drainage layout also matters. Inlet spacing, conveyance bottlenecks, and outfall constraints can cause localized ponding even when average capacity seems adequate. Finally, the exposure pattern, building density, land use intensity, the location of critical facilities, determines what is at stake when streets flood. From a design perspective, this means you can intervene at multiple scales. At parcel scale, you can slow and store water with permeable courtyards, rain gardens, and green roofs. Along streets, you can add roughness and retention through bioswales, tree trenches, and curb extensions that double as storage. At district scale, you can create connected blue-green corridors that move water safely toward storage or outfalls. In other words, the city can behave more like a sponge, not by eliminating runoff, but by delaying peaks and controlling where water concentrates. Before modeling, we should be clear about data needs. At minimum, we need rainfall inputs, observed series, designed storms, and, when planning for the future, climate scenarios. We need a terrain representation, typically a DEM, plus land cover and roughness proxies that influence overland flow. For sewer surface interaction, we also need a drainage network, pipes, inlets, outfalls, and any storage assets like tanks or basins. And to translate flooding into risk, we need exposure layers such as building footprints, critical facilities, population proxies, and asset values. In practice, data come in uneven quality. A litter-derived DEM can reveal curb lines and subtle flow paths, while a coarse DEM may smooth them out. Sewer records may be incomplete, and inlet capacity is often unknown. This is why model purpose matters. A strategic screening study can still be useful with aggregated inputs, as long as outputs are interpreted at the appropriate scale. So the central message is, scale matters. Data resolution and aggregation can materially change screening outputs, but fine data are not automatically better if the modeling question is coarse and uncertain. Fit model detail to the decision scale, corridor, district, catchment, or city, and match the effort to what the decision actually requires. With data in mind, we can choose the right model family. Hydrologic models are often best for rapid runoff screening and catchment scale scenario comparisons, especially when the objective is to compare alternatives rather than map precise street depths. Their trade-off is limited representation of street-scale hydraulics. Hydraulic models, especially coupled 1D-2D approaches, are best when you need sewer surface interaction and spatial mapping of depth, velocity, and hotspots. Their trade-off is higher data requirements, calibration needs, and computational effort. Integrated risk models go a step further by translating flood dynamics into damage, disruption, or vulnerability outputs. Their trade-off is reliance on assumptions beyond hydraulics, such as depth-damage relationships. A practical workflow is screen then zoom. Start with a simpler model to narrow down hotspots and candidate interventions, then apply more detailed hydraulics where design choices require street-level depth and velocity. A simple rule of thumb is to start with the planning question and then choose the simplest model family that can answer it credibly. A practical integrated workflow can be expressed in 6 steps. First, define the decision question and the performance criteria. What constitutes acceptable service, safety, and damage? Second, build a baseline model by assembling data and representing current conditions. Third, test climate and development scenarios, changes in rainfall extremes and changes in land use or density. Fourth, simulate adaptation options, because resilience is about comparing interventions, not only diagnosing problems. Fifth, compare outcomes across risk, cost, and co-benefits. And sixth, translate outputs into design and policy actions, standards, investment priorities, and operations planning. Importantly, this workflow is iterative. New data, revised assumptions, or changed priorities can push the team back to earlier steps, and that is not failure. It is how robust decision-making happens under uncertainty. Also note that stakeholders belong in the loop. Performance criteria should be negotiated with agencies, communities, and infrastructure operators so the modeling outputs answer questions people actually need to act on. Performance-based modeling requires discipline around uncertainty. Calibration means adjusting parameters so the model reproduces observed behavior. such as measured depths, extents, or flow records. Validation tests transferability by comparing model outputs to independent events or spatial evidence not used in calibration. Sensitivity analysis explores which assumptions drive results. In many cities, observed data are limited, and that is precisely why reporting uncertainty ranges and scenario spread is essential. We should avoid false precision. A detailed map can look authoritative even when key inputs are uncertain. It is helpful to separate uncertainties. Input uncertainty, rainfall intensity, DEM errors, model structure uncertainty, how overland flow is represented, and parameter uncertainty, roughness, inlet capture. Good practice is to document the assumptions that matter for decisions, such as roughness, inlet capacity, or rainfall intensities, and to explain how uncertainty could change the ranking of interventions. When communicating results, show ranges and comparative rankings rather than claiming a single, true, depth at every pixel. Risk assessment goes beyond water depth. Hazard mapping includes depth, velocity, duration, and extent because different intensities cause different harms. Fast water can be more dangerous than deep but still water, and long duration can increase property damage and recovery time. Exposure identifies what lies within those hazard zones: buildings, residents, roads, utilities, and critical services. Vulnerability explains why equal hazards do not produce equal losses. A basement apartment, a hospital, and a major intersection have different sensitivity and adaptive capacity. Vulnerability also has a social dimension. Households with fewer resources may have less ability to evacuate, repair, or temporarily relocate, so disruption lasts longer. Impact metrics, expected damage, disruption, downtime, and recovery burden connect physical flooding to planning priorities. This full chain is necessary if we want to prioritize who, what, and where to protect first, and to justify interventions not only technically but socially. Adaptation options span gray infrastructure, blue-green infrastructure, and policy tools. Gray measures include sewer upgrades, pumping, storage tanks, and overflow controls. They often provide clear hydraulic benefits but can be expensive and constrained by space. Blue-green measures include green roofs, permeable surfaces, bioswales, tree pits, detention basins, and restored corridors. These measures can reduce runoff generation and slow flow while delivering co-benefits like heat reduction, biodiversity support, and improved public space. Policy and operational tools include zoning and land use controls, maintenance regimes for inlets and channels, emergency planning and early warning, financing strategies, and governance arrangements. When assembling a portfolio, consider lifecycle performance. For example, a bioswale that is not maintained can lose capacity, just as a pipe can clog. And consider distributional impacts. If upgrades protect a high-value district first while leaving vulnerable areas behind, risk may become more inequitable. To compare measures fairly, pair hydraulic metrics, depth, duration reduction, with service metrics, route continuity, facility downtime, and co-benefit metrics, public space quality, heat reduction. This makes the portfolio logic transparent. Simulations make adaptation choices comparable because they let us evaluate the same place under multiple futures and intervention mixes. Start with a baseline representation of the current system. Then represent urban growth, new density, changed land use, new imperviousness. Add climate futures, changed rainfall regimes, potentially different storm durations and intensities. Finally, represent an intervention portfolio that mixes gray, blue-green, and policy changes. When you run these combinations, you can compare outcomes, where hotspots persist, where interventions shift risk downstream, and how benefits vary across neighborhoods. A useful habit is to define comparable metrics, such as flooded road length above a threshold depth, number of critical facilities affected, or expected downtime. These metrics allow decision-makers to compare portfolios even when maps look different. This turns what-if debates into structured comparisons, while still acknowledging uncertainty and assumptions. A frequent planning mistake is to treat climate change and land use change separately, or to consider one as an afterthought. In reality, they interact. An intensifying rainfall signal can change design storms and return period assumptions, meaning that infrastructure designed for historic storms may be undersized sooner than expected. At the same time, urban expansion, vegetation loss, or deforestation can increase runoff and flood peaks even if rainfall statistics were stable. When both changes occur together, the result can be non-linear. Small increases in rainfall intensity combined with additional imperviousness can produce large increases in peak flow and inundation. Best practice is therefore to evaluate climate and land use change together in the same scenario matrix so that decisions are future-ready rather than anchored to the past. Resilience means more than protection. Protection and robustness are important, resisting flooding without major performance failure, but resilience also includes redundancy, backup pathways, alternative routes, and distributed storage that prevents single points of failure. Rapidity matters. How quickly mobility, safety, and essential services are restored after an event. Resourcefulness reflects coordination, information flows, institutions, funding mechanisms, and the capacity to adapt. Designers can contribute directly. For example, by ensuring critical routes have redundant detours, by creating public spaces that can safely flood without major damage, and by designing buildings and ground floors for wetting and fast recovery when flooding cannot be fully avoided. A city can build larger pipes, but if emergency access is blocked or recovery is slow, the city is not truly resilient. Emerging tools can strengthen this whole approach when they serve decisions. GIS is foundational because it combines terrain, drainage, land use, and exposure in a single spatial workflow and supports reproducible scenario management. Remote sensing and crowdsourced observations can expand situational awareness, especially for validating extents and understanding where water actually accumulates. AI can accelerate forecasting and rapid scenario exploration, but outputs still need transparency and checks against physical logic. Digital twins connect monitoring to modeling to management. They enable iterative updates of assumptions, rapid retesting under new conditions, and adaptive planning as cities change. In practice, this works best when you define an update cadence. What data are refreshed monthly, seasonally, or after major events, and when roles are clear. Who owns the data, who runs the models, and how decisions are triggered by thresholds. The key is to use these tools to shorten feedback loops between evidence and action. Ultimately, models are only valuable if their outputs become decisions. Flood maps identify hotspots, extents, depths, and durations. From these, teams define risk thresholds. What levels of flooding are acceptable for different street hierarchies, land uses, and critical facilities? Those thresholds translate into design rules. Street sections that provide safe conveyance, parcel-scale storage requirements, zoning overlays for high-risk areas, and protection standards for essential services. For example, a city might set a threshold that primary emergency routes should not exceed a shallow depth for more than a limited duration in a specified design storm ensemble. That threshold then drives where storage, curb inlets, or pumping is needed. Equally important, these thresholds should be checked for equity. Do they protect vulnerable neighborhoods and essential services first, or only where property values are highest? Model outputs also support priority site selection and a monitoring and update loop as data and climate assumptions change. Best Case 1 illustrates why coupled 1D-2D modeling can be essential in extreme events. In Zhengzhou, the approach used a platform such as InfoWorks ICM to couple sewer dynamics with surface flow. Instead of relying on a single design storm, the study combined 6 rainfall scenarios varying return periods and storm durations. Outputs assessed depth, extent, duration, and hotspot locations, helping identify which areas repeatedly fail across scenarios. The design lesson is that low-lying areas and infrastructure near river corridors and roadbeds require focused monitoring and targeted countermeasures. More broadly, scenario ensembles reveal where land use controls, drainage upgrades, and emergency access routes matter most. The key takeaway is that a single storm assumption can hide vulnerability. Resilient decisions often require exploring a family of plausible extremes. Best Case 2 focuses on screening and the sometimes counterintuitive role of data resolution. The study linked aggregated building data, imperviousness, and flood damage to support strategic screening when detailed development inputs are not available. It explicitly tested how spatial resolution influences model identifiability and robustness. The practical message is that finer data are not automatically better for strategic screening. If the planning question is coarse, or if development scenarios are aggregated, extremely fine inputs can create a false sense of certainty without improving decision relevance. Matching model scale to planning scale can save effort and produce outputs that stakeholders can actually use. To close, remember 5 takeaways. Urban flood resilience depends on linking climate signals, urban form, infrastructure capacity, and recovery. Model choice should match the decision question, the scale, and available data, not simply the most complex option. Risk assessment must combine hazard, exposure, vulnerability, and service disruption if we want defensible priorities. Mixed portfolios that blend gray, blue-green, and policy measures are typically stronger than isolated interventions and can deliver co-benefits. Finally, digital workflows matter most when they shorten the loop between evidence, design rules, investments, and adaptive management. As you apply these ideas, aim to be explicit about assumptions and inclusive about who defines acceptable risk. Thank you.